phi is well defined. We proved phi is linear, phi is 1, 1. Now we are proving in the fourth step phi is isometry. That means we have to prove norm T star is equal to norm T. So in the equation 1, we have already showed that norm T star is lesser than or equal to norm T. We have to prove now norm T star is greater than or equal to norm T. Now, let us take any element in X which is non-zero, and whenever X is non-zero, therefore T of X will be non-zero. T of X will also belong to N itself. N is the non-linear space. So by one of the applications of Hahn-Banach theorem, we have functional belonging to N star such that functional on that non-zero element. The non-zero element we are taking here is T of X. So T of X equal to norm Tx, and norm of F naught equal to 1. Now again I consider norm T star. What is norm T star? It is supremum of norm T star F such that norm F is lesser than or equal to 1. That is equal to supremum. This is norm T star F of X. I'm combining two supremums into one, just like the previous step. And norm X is lesser than or equal to 1. Okay. So this is our norm T star is equal to this. And what is F? F is any functional belonging to N star. This is happening for all F belonging to N star such that norm F is less than or equal to 1. We have an F naught here. We have an F naught here belonging to N star whose norm is equal to 1. So therefore, norm T star, which is supremum of all such functionals and such elements X, and we have one element this side, that is this T star F of X is nothing but F of Tx, using the definition of T star. So we have one such F naught here, F naught, and taking T of X. Okay, we take the norm of this. So this is supremum of all such functionals and such elements X here, and this is one element F naught belonging to N star, and norm F naught equal to 1. So this will be, by definition, it will be greater than or equal to this, and F naught of T of X is nothing but norm Tx, which is equal to norm T of X. So I rewrite it. So norm T star of X is greater than or equal to norm Tx such that norm X lesser than or equal to 1 for all X belonging to N with norm X lesser than or equal to 1. So this also will be greater than or equal to supremum such that norm X lesser than 1 or equal to 1. Okay, and this is nothing but the definition of norm T. So therefore, LHS norm T star is greater than or equal to norm T. We call this as T. So by 1 and 2, norm T star is equal to norm T. Therefore, norm phi of T is equal to norm T. Therefore, phi is isometric. So step 4 is over. Now, by step 2, step 3, and step 4, phi is isometric isomorphism. Isometric isomorphism. This is part of the theorem is over. Now next, two things we have to prove. We have to prove phi preserves identity, and then we have to prove phi reverses the product. Now we shall go to the next step now. So the next step, step number 5, we shall prove that in step 5, to prove that phi preserves identity. Phi preserves identity. That is to show that phi of I identity map is itself. That is phi of I is I star equal to I. Now to prove this, let us consider I star of f of x, which is nothing but by definition is f of I of x. I of x is nothing but x itself, and f of x, we can just have I into f of x. What is our LHS? I can write f of x as I into f of x. So what is our LHS? LHS is I star of f of x is equal to I of f of x for all f and for all x. So therefore, I star equal to I. So therefore, we proved phi preserves the identity map. Okay, now the last step, the sixth step, to prove that phi reverses product. Phi reverses the product. So let us take two, T1 and T2, two operators. Okay, consider phi of T1 into T2. I'm taking the product of two operators, T1 and T2. By definition, this is nothing but T1, T2 star. So T1, T2 star should act on F on X. So by definition, this is nothing but F of T1, T2 of X. That is nothing but F of T1 of, look at the bracket, T2 of X. Now, using definition backwards again, this for T2 I'm using the definition. So T2 will come out now. So T2 star F of T1 X. Now T1 will come. That is T2 star T1 star F of X. And this happens for all F and all X. So I'll take away F and X now. So T2 star T1 star. So therefore, we have got T1 T2 whole star is nothing but T2 star T1 star. And this is nothing but phi of T1, T2. T1, T2. Now the product is got reversed. So hence we proved that. Therefore, phi reverses product. So we proved phi reverse identity, phi reverse product. We proved it is isometric isomorphism. So this ends the theorem. Ends the theorem.